Hello there, Energy 301 students. This is Dr. John Schrage, and I thought I'd record today from beautiful Hobstadt, Indiana. This is this town where my wife has her practice. She's a dentist, as I've mentioned before. And I don't know, not to engage in any stereotypes or something, but I was like, fields, it'll look lovely to have that in the background. I'm having some trouble with my microphone today, so I had to use this external one. So I apologize that I've kind of got this thing stuck in my face here. I know that it's a bit of a stereotype to do this kind of thing on the first day of class, but I thought I would kind of parse through what the name of the course actually means. I mean, the name of the course is Modeling Electrical Load and Yield, and it can be a little tricky to understand. I mean, when you see what's going on in the class, how is that modeling electrical load and yield? Well, okay, I think the word modeling, I think we have a sense of what that means, but actually there can be lots of different types of models. I mean, I think you understand the word modeling to mean something like simulating or forecasting or something like that. But actually there's a whole lot of different kinds of models out there, like a conceptual model. A conceptual model is a model made of the composition of concepts which are used to help people know, understand, or simulate a subject. Now, a simple example I could give for you that would be like a model of the hydrologic cycle. This is a simple model. It's a conceptual model. It's just sort of showing us how all these pieces work and how they interact. I mean, we can see that there's runoff of water, and there's evaporation of water, and there's precipitation, and we kind of see how all these processes link and interact with each other and so on. Conceptual models are often not necessarily a science thing. I mean, there could be a conceptual model of like a philosophical idea or a political position, or maybe of like how a business is going to work or something like that. Conceptual models are certainly used in science, especially in teaching science. They're like how a scientist might develop their hypotheses or something like that. But they don't necessarily lead to us like any kind of quantitative forecast or something like that. We want to start kind of narrowing ourselves down to more scientific types of models, where scientific modeling aims to make a feature of the world easier to understand, define, quantify, visualize, or simulate. For example, here's a common ball and stick type model of a molecule. Real molecules don't look like that. This is not a model of a molecule in the sense of it physically looks like a molecule. But it helps us understand how the molecule is actually structured and how the different parts of the molecule function. Another example of a scientific model would be like this very elaborate simulation of ocean currents at the surface. I mean, it's taking a lot of simplifications. How they actually came up with what the ocean is doing here in this model could be very complicated, could be very simple, but either way it tells us a great deal about how the ocean is functioning. What is the ocean actually doing here? Here's another example of a scientific model. This is just a simple little piece of software that simulates the orbits of the planets. And here you could use this simple model that is simulating the behavior of the planetary system to come up with quantitative estimates of the location of the planets at some time in the future or the past. These are all examples of different kinds of scientific models. An example of a type of scientific model would be a physical model. Physical models are either larger or smaller versions of real objects that are used to describe the behaviors of the objects under controlled conditions. When I teach about models to like the introduction to atmospheric science classes, I like to first start with like model trains. Honestly though, to be honest, model trains, they're a smaller version of the real train. There aren't that many useful things you could learn by using a model train to learn about what real trains are doing. I mean, I suppose you could like simulate the patterns of traffic using these physical models of the train. Maybe you could learn something about like how sharp of a curve the train can go around, based on the couplings between the trains or something. If you knew nothing about trains whatsoever, you could learn a thing or two about trains using this physical model. You could learn about how they couple together, or that they can't go upside down or anything like that. I mean, but the limits of what you could learn from a physical model of, say, a train are pretty strict. On the other hand, for example, like a wind tunnel. Now, a wind tunnel is a type of physical model. You could be putting in a smaller version of a real airplane and learn certain things about like the aerodynamic properties of the airplane in the wind tunnel. You could be learning about like, the lift it generates, since its wings generate at different air speeds and so on. This model would be a lot easier to work with than, say, a real jumbo jet, and a lot safer and so on. And so you could learn a lot about the actual you know, device from this physical model. Thinking in terms of electrical load and yield, I mean, I don't think anybody actually does such a thing, but you certainly could simulate use a physical model of like a neighborhood to simulate like heat loss. You know, you could make it so that these little model houses lose heat in ways similar to the way real houses do, and then under different conditions, maybe you could run air over, you know, fans over the village and see how it's losing heat, and you know, a physical model that could simulate like, you know, the heating needs of this neighborhood or something like that. I don't know that that's actually done, but I mean, as kind of a straw man here, we could say that that would be a strategy. You could do it. On the other hand, you know, in modern science, a lot more of our modeling is done as computer models. Computer models are sets of algorithms that reproduce the behavior of a system based on the physical laws. This is the core way in which we do meteorology. Meteorology is mostly nowadays numerical weather prediction, or NWP. Numerical weather prediction is how most forecasts are produced these days, where we start with computer programs that know the so-called 7 primitive equations in meteorology that describe changes in temperature, changes in densities, changes in pressure, changes in the different components of the wind, and so on. Atmospheric science majors know all about this kinds of stuff. It's kind of the core of what they learn in their education. And numerical weather prediction models encapsulate that knowledge into an algorithm to make forecasts of what the weather is going to do. It's a computer program that embodies that knowledge to make predictions. You could do the same sort of thing, like for example, this is a simulation of hot spots in the Earth's mantle and how they formed islands. Okay, they used fluid mechanical equations to simulate how the magma is moving. They took into account all the different processes at work, like probably things like the first law of thermodynamics and various continuity type equations for how the magma was moving. And as long as the computer program knew all those equations, it was able to make a simulation as to how a model of how those hot spots and those plumes were working in the Earth's mantle. Those things are all pretty cool, but they're not quite what we're doing in this class. What we're going to be working with this class is learning how, I mean, don't get me wrong, we'll do some of these kinds of things too, but more to the point, we're going to be learning about statistical models. Statistical models are calculations based on observations and observed data and assumptions about the nature of the physical process that's being simulated. We're using the past behavior of the system to tell us something about what we should be expecting for future behaviors of it. For example, look at this little graph here. I just downloaded this from anywhere. This isn't real data. This is just some random numbers, I'm sure, with some trend imposed on it. But you know, you could say maybe on the y-axis you had temperature, and I'm sorry, x-axis maybe is temperature, and the y-axis was electrical load on the grid. And you would be able to see how, you know, each day's electrical load varies quite a bit, but there is sort of a trend to it with the temperature. You could say that that regression line, that best fit line that's through there, is a type of model. It's a type of statistical model. It's saying for this temperature on the x-axis, this is what I'm predicting on the y-axis for the electrical load. You know, maybe as the temperature goes up, due to air conditioning, the electrical load goes up. That would be an example of a statistical model. And they're all very quantifiable, and they can be tested in a hypothesis testing kind of way. And that's what a big chunk of this class is going to be about, is how these statistical models work in all kinds of different applications. Here's another little statistical model that's a more complicated nonlinear model, where, like, again, let's just say we had temperature on the x-axis and electrical load on the y-axis. Well, now we have a more complicated nonlinear relationship where, like, at very low temperatures the electrical load is high, maybe due to electric heat being used in that neighborhood. At some range of temperatures the electrical load is quite low because, you know, the weather is fine and people have the windows open, they have the air conditioning off, and so on. And then at high temperatures the electrical load starts going back up because now we are running a lot of air conditioning. Okay, that again, that curve that they fit through that line, that's an example of a statistical model. It's using the past behavior and the observations of the temperature versus the electrical load to determine the, to come up with an estimate anyway of what the electrical load will be under a given temperature. And again, we can put error bars on this, and we can hypothesis test this to find out if it's statistically significant and so on. And these kinds of ideas make up statistical modeling. Most of what we're going to do this semester is going to be statistical modeling, just because that's kind of, the other kinds of modeling are kind of what happens in other courses. Okay, continuing our idea that we're going to be parsing what these name of this class means, let's talk about electrical load. And generally, this is going to be the power that's consumed by a circuit. Um, we're going to be looking at this, not necessarily an individual circuit. We're talking about like the electrical load. What is the consumption of the power by a house or by a neighborhood or, for a power company or something like that. And this is in part going to be determined by weather, as that is, of course, a major part of what drives power consumption. I mean, obviously in the winter, there's going to be a lot of heat that is going to be needed. Now, you would have to know more about like the economic, where do people get heat in your domain? If it's coal, if it's gas, if it's electric, if it's heating oil, whatever. And in the same way, in the summer, you would need to know about like air conditioning and air conditioning usages and so on. But clearly, the amount of air conditioning that is needed depends a great deal on the weather. And so the electrical load will be a function of the meteorology of the situation, as we're going to be seeing. In contrast, electrical yield is going to be the power that is generated by a circuit. Now, we could be talking that in the context of like a natural gas power plant, where we could talk about the yield of that plant or something like that. But since this class has a connection to atmospheric sciences and environmental sciences and so on, we're going to be focusing mainly on production of power by renewable sources like production of power by like the solar and by wind. I mean, obviously these are very closely related to ideas that are, meteorology. I mean, obviously, like for example, the amount of solar power that is being generated by a solar power panel depends on things like the clouds in the area. It depends on things like fog and visibility and air quality, all of which can attenuate the solar radiation that is reaching the solar panel. It also is dependent on geometry. We'll be learning more about the geometry of how you decide, how to configure your panel to get the maximum amount of solar radiation that can be converted. That also depends on factors that are related to climate, like latitude and so on. So let me go ahead and kind of build a little model here as to how I want this all to work. Oh, yeah, I'm kind of building a little conceptual model how I think of this as working here. I mean, obviously weather and climate is very related to both the electrical load and the yield. I mean, strictly speaking, it probably wouldn't be necessary to model the electrical load for a given weather condition at all. I mean, I suppose, strictly speaking, you could go ahead and like outfit every house in the neighborhood with sensors to measure, how insulated it is and how efficient the furnace is and so on, and you could literally explicitly compute what its demand will be under different conditions. But frankly, good luck with that. You'll never get all that permission here. Another strategy you could do is, if you were going to try to model the electrical load under different weather conditions, is I suppose you could build a little physical model, make little model houses, and then measure the heat loss under different conditions in the lab. You could even do this like with regard to production of power. I mean, you could maybe make little solar panels and little wind turbines and try them under different conditions and so on, and that probably is actually part of the process of developing such a system. But obviously it would be more likely to use like a computer model. Computer models would be gathering information about like the composition of the wall, the insulation, and so on, and then you would be, using the physics of the situation to actually estimate the heat loss through the walls and so on under different weather conditions. Or you could use the physics of the situation to simulate the wind turbines and the solar cells and so on to be estimating the power yield under different weather conditions. And all of that could be done, but realistically a much more efficient strategy is going to be using statistical models, where you're going to be using past observations of electrical load under different conditions to produce estimates of future electrical load. You could do the same thing to make estimates of different amounts of power production, where you're saying, okay, under these conditions we produce this much power, so we can assume that similarly we'll be able to make a certain amount of power under these weather conditions and so on. Weather forecasts then are going to be intrinsically important to how all of this works, and these weather forecasts are going to be made using computer models, which themselves are based on the physical laws, like the 7 primitive equations, things like the first law of thermodynamics and the continuity equation and Newton's laws and things like that. So what we're going to be doing here is we're going to start with a basic understanding of how the atmosphere works. We're just going to kind of be plowing through some very basics of atmospheric science. At the present time, ATS 113, the Introduction to Meteorology course, is not a requirement for the energy program. It may be in the future, but at the present time it is not. And so the plan for the class is that one module of this class will be about basics of meteorology, so that you have terminology and you understand the basics of the forces and so on at work. And we'll fill in gaps in this as we go through over the course of the semester. But you're going to be learning at this time then about things like temperature, pressure, humidity, clouds, precipitation, etc. And then you're going to use that as a physical background as we learn to use statistical tools like regression and so on to produce forecasts of electrical load and yield. Okay, so what we do here after the end of this first little lecture that's sort of just an overview of what models are and so on, is we're going to then take this and we're going to move forward and start talking about just kind of a quick breeze through the physics of the atmosphere. This is not going to be anything all that technical. We're going to talk a little bit about temperature, including like the basics of radiation in the atmosphere and so on. And we're going to do pressure and the winds. We're going to talk a little bit about moisture and the formation of clouds and precipitation and so on. And that'll just get us to the end of this first module in the class. After that, we'll start getting more into the statistics. We're going to start writing little programs and so on. But this first little module is just sort of a background in meteorology, especially the physics of meteorology. We'll learn more, like I said, about meteorology and wind profiles for use in wind turbines and things like that as we go through the semester, but this little overview will help. Okay, please let me know if you have any questions. This has been Dr. John Schrage.